Imagine someone tells you an object exists in space, does the math to prove it, and then nobody sees it for almost 200 years. Sounds crazy, right? But that's exactly what happened with black holes. The idea showed up on paper in 1783. The first real evidence didn't arrive until 1971. That's nearly 2 centuries of this should be out there somewhere before anyone actually caught one. So here's a question worth sitting with. What else is currently just an idea on a chalkboard, waiting for its turn to be discovered? Today we're going on a tour of the strangest, most mind-bending objects that physics says could exist: stars made of pure vacuum, holes in space that spit things out instead of swallowing them, and maybe even entire universes running parallel to our own. None of this is confirmed. All of it is backed by real math. Let's get into it. Before we get to the weird stuff, you need to know one basic rule: every star is in a tug-of-war. Gravity is constantly trying to crush it inward, and something else has to push back just as hard, or the whole thing collapses. In our Sun, that pushback comes from the energy released by fusion in its core. Once the Sun runs out of fuel, billions of years from now, it'll shrink down into a white dwarf, a leftover core with no fusion happening at all. So what stops that from collapsing further? A strange rule from quantum physics called electron degeneracy pressure, which basically says electrons refuse to be squeezed too close together. But that rule only works up to a point. Push past about 1.4 times the Sun's mass, and even that quantum resistance gives out. The core collapses further and forms something even stranger, a neutron star, held up by neutrons themselves refusing to be crammed together. Push past roughly 2.2 solar masses, and even that fails. At that point, nothing known in physics can stop the collapse. What's left behind is what we call a black hole. Here's where it gets interesting. In 1959, a physicist named Hans Buchdahl proved that any normal star made of ordinary matter with regular pressure can never be smaller than 9/8 of the size a black hole of the same mass would be. That gap is actually useful, because it means real stars and black holes should always look noticeably different in size. But Buchdahl's rule has a loophole: it only applies to matter that behaves normally. What if a star were made of something where pressure goes negative? Then that size limit disappears completely, and the star could shrink down almost exactly to the size of a black hole, close enough that from the outside, you genuinely couldn't tell them apart. Physicists worked out the math for exactly this scenario using something called the TOV equation. And the result is bizarre: for this kind of star to stay stable, its internal pressure has to spike to negative infinity somewhere inside it, flip instantly to positive infinity, and then taper back down to 0 at the surface. There's exactly one special case where this doesn't blow up, and in that case, the pressure and energy density stay locked at equal and opposite values all the way through the star. If that sounds oddly familiar, it's because those are the exact properties we associate with dark energy, specifically vacuum energy. That's why scientists nicknamed this hypothetical object a gravastar, short for gravitational vacuum star. Step inside one, and you'd feel nothing at all: no pull inward, no push outward. You'd just float, exactly as if you were floating in empty space itself. And here's the part that really gets physicists talking: some researchers have floated the idea that gravastars scattered throughout the universe could actually be the dark energy that's been accelerating cosmic expansion for the last 5 billion years. A 2023 study out of the University of Hawaii even found that massive black holes seem to be gaining mass at a rate suspiciously close to what you'd expect from dark energy growth. It's a genuinely exciting idea, and it's also been heavily disputed by other astronomers, so don't take it as settled science. It's a live argument, not a done deal. Now let's flip everything on its head. A black hole lets things fall in but never lets anything out. Physics also allows for the exact reverse: an object that lets things escape but never allows anything to enter. That's a white hole. This isn't science fiction, it falls directly out of the same equations that describe black holes in Einstein's general relativity. When physicists map out the full mathematical structure of an idealized, eternal black hole, the solution doesn't just include the black hole itself. It also includes a white hole, and even a separate, causally disconnected region that looks like a parallel universe. That doesn't mean every black hole out there has a white hole attached to it. Real black holes form from collapsing stars, which breaks a lot of the clean assumptions the math relies on. But the concept itself is completely valid physics, it's just that no confirmed white hole has ever been observed. There's actually a newer theory worth mentioning. Some researchers working with an approach called loop quantum gravity suggest that once a black hole shrinks down to an almost unimaginably tiny mass through Hawking radiation, it might not vanish completely, it could instead tunnel into a white hole and release everything it swallowed back into the universe. If true, this could even help solve one of physics' oldest headaches, the black hole information paradox, the puzzle of whether information that falls into a black hole is truly lost forever. Let's zoom all the way out. Our universe is expanding, and that expansion is speeding up, driven by dark energy. Scientists have actually measured how strong that dark energy needs to be to match what we observe. But here's the strange part: when physicists try to calculate that number from theory using quantum field theory, their prediction comes out roughly a trillion times too large. If the real universe actually had that much dark energy, space would have ripped itself apart before stars or galaxies ever had the chance to form. We wouldn't exist to ask the question. So why is the real number so much smaller and so precisely tuned for galaxies, stars, and eventually us to exist? One idea is pure coincidence layered on top of unknown physics that cancels the math out. Another is intelligent design. But a lot of physicists lean toward a third option: maybe our universe isn't the only one. If there are countless universes out there, each with a randomly different amount of dark energy, then most of them would be lifeless wastelands or would have collapsed instantly. But a small fraction would happen to land in the narrow range that allows galaxies, stars, and life to form, and naturally, those are the only universes anyone would ever be around to observe. This is called the anthropic principle, and it doesn't require the universe to be fine-tuned on purpose. It just requires enough universes that at least one lucky roll of the dice happens. Physicists actually describe a few different flavors of multiverse: one from an eternal cycle of big bangs and big crunches, one from regions of space too far away for light to ever reach us, and one from quantum mechanics itself, where every measurement splits reality into branching outcomes. None of these have been proven. All of them remain live, testable in principle ideas. So, are any of these real? Gravastars, white holes, parallel universes? Right now, we genuinely don't know. But that's the whole story of black holes too. An idea on paper for nearly 200 years before anyone ever saw one. Science has a track record of turning "that's just theoretical" into "that's just Tuesday." Neptune, antimatter, the cosmic microwave background, all of it existed on a chalkboard before it ever showed up in a telescope. So maybe the next time someone tells you something is only a hypothesis, it's worth remembering, sometimes a hypothesis just means we haven't looked hard enough yet.